This video is going to focus on how to determine an Ionic formula. So the first thing to do is, what is the meaning of the term formula? Now, probably the best way to imagine this is to think if someone asked you, what is the formula of water? Instantly, you probably reply H2O. And the reason why you know that formula so well is because it's so ubiquitous to our society, and we use it so often, it's become ingrained in our psyche. But if we break that idea down, we can probably work out what a formula actually means. Because what you've done there is you've represented a molecule of water using the symbols of the different elements that it's comprised of. And not only that, you've also thought about the relative proportions of those different elements inside a molecule of water. Essentially, a molecule of water contains 2 atoms of hydrogen and 1 atom of oxygen. The 2 atoms of hydrogen are bonded to the 1 atom of oxygen via covalent bonding. So if we apply that idea of what a formula is more widely, we can see that any formula will be a representation of a chemical substance using the symbols for the different elements found in the periodic table, but making sure they're in relative proportion to each other. So how does that then apply to the idea of an ionic formula? And how is that different? Well, the key difference is the term ion. And you've got to understand what an ion is. And if you think back to what the meaning of the term ion is, you might remember that it's basically a charged variant of an atom or a molecule. Atoms or molecules become charged because they have either lost electrons or gained electrons, and they come in 2 flavours. There are positive ions and negative ions. If an atom or molecule loses electrons, it becomes positively charged, and the other name for that is a cation. If an atom or molecule gains electrons to become charged, then it becomes a negative ion, or in other words, an anion. And the key thing about an ionic formula is that you have to ensure the ionic charges found within your formula, your compound, actually balance each other out as a total, leaving you with no overall charge. There are many ways of doing this. There are multiple methods and approaches to this. I'm going to show you as many as I can, and hopefully you'll pick at least one of them to carry on with, whichever one you find the easiest to use. The first one is quite nice and pictorial, and it's called the ions in a box method. So an example could be sodium sulfide. The first thing you need to know is what is the charge of a sodium ion and a sulfide ion. And this can be determined for simple group-based elements on the group number. So sodium is a group 1 element. That means it has 1 electron in its outermost shell. So when sodium atoms react with a non-metal, they will give away that outermost electron to become more energetically stable. In doing so, they will gain a full outer shell because they will go down to the next shell below, which is full. The great thing about the group system is that every other element in that group will behave in a similar way. So it's not only sodium that forms +1 ions, but also potassium and lithium and all the others as well. The reason why it's a +1 ion is because it still has the same number of protons in its nucleus it always had, in the case of sodium 11. But now it's lost that outer electron, it only has 10 negative electrons surrounding that nucleus. So the overall charge of that particle as a whole is +1. A similar approach can be taken for sulfide ions as well. Sulfur is a group 6 element, and so it has 2 options energetically to try and form that more stable full shell configuration. Sulfur could lose 6 electrons or gain 2 electrons to gain that full outer shell. Energetically, it would be easier to gain 2 electrons. So sulfur gains 2 electrons when it reacts with a metal, for example, and becomes a sulfide 2- ion. It's 2- because there is an imbalance in charge between the number of protons and the new number of electrons. There are 2 more electrons, hence overall there is a 2- charge. Once you know those charges, I've turned those ions into little tokens, and I've drawn myself a box and I start putting my ion tokens into the box. If I put 1 sodium +1 token and 1 sulfide -1 token into the box, and consider the overall charge that those 2 ions together in the box bring, I realise that they don't actually equal 0, because +1 - 2 is -1. And that's not right, because I'm looking for my formula, my overall combination of ions, to have no overall charge. So what I do is I bring a second sodium counter or ion or token into the box, and I redo my calculation. This time I have 2 single pluses and 1 2- token. +1 + 1 - 2 equals 0, and that's right because there's no overall charge. I rewrite my findings as a simple formula. Na subscript to S, there are 2 sodiums to every 1 sulfide ion in this compound. That's one method. The second method, which is a kind of a bit of a cheat really, is called the swap and drop method. Some people like this and some people don't, because it can sometimes feel like a bit of a cop-out, but it's a nice, simple cheat method, if you like. You simply write the ions down once you determine their charges next to each other. There's my sodium ion and my sulfide ion. And then you swap and drop. You swap the charge in the position above the symbol there, okay, in the superscript position. You swap it across to become subscript next to the other element. So I take my 2- charge for sulfur and bring it down below subscript next to the sodium. I bring my +1 charge, which essentially is 1+, and make it subscript next to my sulfide. And then what I've realised is I've just created this formula, Na2S, and that happens to be the correct formula for sodium sulfide. Probably not the preferable method, because there's not much real theory and arithmetic behind that method, but it is useful if you're in a rush. The third way of thinking about things is a number line. This can be useful if you struggle to remember or recall how positive and negative numbers work, and it might help you to realise how to get to neutrality. So again, we're trying to get to a position of 0 charge. So what I've done here is I've first of all drawn on a line which represents me putting down 1 sulfide ion, and it takes me down to a -2 value overall. I've then drawn a second arrow going upwards in a positive direction for one of my sodium ions being placed into this situation. And I realise it only takes me as far as -1. So I bring a second 1+ sodium and I draw a second arrow, and it brings me back to neutrality. And then I realise I've reached my goal of making sure my formula has no overall charge. So it would be, my formula needs to contain 2 sodiums to every 1 sulfide. In other words, Na2S. So number lines can help you to visualise positive and negative number. Finally, guys, there are such things as polyatomic ions. Now, polyatomic ions are more complex molecular ions. They're often negative, but sometimes they're positive, like ammonium ions. And the thing to really realise about this is, you'll have to memorise a few of these for most exam courses. These 5 are very common. And the second thing to realise is they behave in terms of our sort of accounting system in exactly the same way as the simple monoatomic ion examples. So we've got hydroxide, OH-, carbonate, CO3, 2-, sulfate, SO4, 2-, nitrate, NO3-, and ammonium, NH4+. And these are all molecular packages that have this overall charge. So the whole NO3 total has a -1 charge. So all you do when you're doing your accounting system, and I'm using the box method again, is rather than writing just S2- for a sulfide ion, if I was doing a sulfate ion, I write the whole formula of the molecule in my token and include its charge. And as long as I realise that that's a package and I can't split it into sulfur and oxygen separately, then it should still be absolutely applicable. So imagine I was trying to work out the formula for aluminium sulfate. Aluminium is a group 3 element and therefore forms a +3 charge, and sulfate ions have been memorised by me as -2 ions. So I could put an aluminium token and a sulfate token in my box, and that's +3 -2, and I get an overall charge of +1. And I realise that's not quite right. I'm looking for no overall charge. So I start putting more tokens into the box. So what if I put 1 aluminium and 2 sulfates into the box to try and get rid of all that positive charge? The problem is now that I overshoot, because I've got +3 and -4 with those 2 -2 ions, giving me a 1- charge overall. And again, that's not quite neutral. So how about I retry again? What if I put 2 aluminium ions and 2 sulfate ions in? And again, that doesn't quite work, because that gives me 6+ and 4-, and therefore that's +2 overall. So the only thing I can do is keep going till I get to neutrality. What if I put 2 aluminiums in and 3 sulfates? So I put 2 aluminium ions into the box, giving me an overall charge of +3, +3, 6+. 3 sulfate ions, which each is -2, -2, -4, -6. Well, that's great, because I've got 6+ charges with the 2 aluminiums and 6- charge with the 3 sulfates, and that equals 0. And that's therefore a neutral and correct formula for my ionic compound. All I then do is convert it into a formula, Al2SO4 3. Now, you might notice I've put some brackets around the SO4, the polyatomic ion. The reason for that is because if I hadn't, what I would have written would have read Al2SO43. And unfortunately, that's not what I was trying to say. That would have meant I had 2 aluminiums, 1 sulfur, and 43 oxygens. So by putting a bracket around the SO4 polyatomic ion, I am conserving that. I'm keeping it together and saying that for every 2 aluminiums, there are 3 of the whole SO4 package. And then that is the correct formula for that compound. So hopefully that helps you guys to understand exactly how to balance ionic formulae for the future.